Welcome in the arena. My name's Allyson Klein. We're coming to you from the Accelerated Computing Conference in New York. And this is a Data Insights episode. So that means Jeniece Wnorowski is with me again. Welcome back, Jeniece.
Thank you, Allyson. It's great to be back.
So we have been talking about quantum all day long. It's been blowing my mind. And you brought a fantastic guest with us to give a perspective on where we are with the quantum journey that is deeply rooted in the classical computing arena. So tell me about who you have next to you and what we're going to be talking about.
Yeah, I'm excited because we've talked a lot to, different organizations, startups, kind of incubator type companies. But today we're going to hear from Dell. So with me, we have Burns Healy, who's head of infrastructure for Dell's quantum computing division. So welcome to the program.
Thank you so much for having me. I really appreciate the opportunity to speak with you.
So Burns, I got to start. So Dell, obviously known as one of the largest classical computing companies in the world, but you're working in quantum, which is fascinating. Tell me a little bit about how Dell is involved in quantum and what your role is.
Yeah, so that's a great question. And I know that there's a lot of quantum-specific companies that are here and represented. And as you mentioned, we're mostly classical compute. But I think a key point that it helps for us all to remember is that this doesn't exist in a vacuum. Quantum computers are almost a bit of a misnomer when you say quantum computer. I prefer to use the term quantum accelerator because really that's what they are. They're an add-on to HPC or data center infrastructure that give you specialized options for computing specific workloads. So in that sense, you don't have quantum computers without classical computers, and we're helping to accelerate those by producing the best supporting ecosystem and infrastructure appliances that we can.
There's a growing conversation about where quantum fits into the broader compute landscape. How do you think about its role today alongside more kind of established computing approaches?
Yeah, that's a great question. And I think that the key in my mind is that it will continue to grow and expand as the devices mature. There'll be a handful of cases, even today, where you'll see quantum accelerators make an impact, make a difference, and provide some sort of advantage in various problems over traditional approaches. And as we go into 2027, up towards 2030, 2035, that window will just kind of grow, and the places where you can actually divert workloads from classical systems to quantum will become more adopted, they'll become more well understood, more optimized, and it's just an exciting time to watch those begin to come online and subject matter experts in different verticals understand the power of quantum algorithms and really begin to tweak them for their own purposes.
Now, traditional conversations around quantum have really focused on physical qubits and error rates and how are we going to scale physical qubits and drop error rates? Now you're starting to hear things like logical qubits and error correction. Help make sense of this. Tell me about how that shifts the way that we should think about what usable quantum is.
Yeah, absolutely. So even in the classical computing realm, we use things like error correcting code, which is a way of running applications that are more resilient because there's an understanding that in the event of something funky going on, they are not liable to crash because there are kind of fail-safes built in. I'd liken logical qubits to getting to that error correcting code schema of classical computing, where we say we understand the fundamental kind of qubits, the actual underlying architecture, and just the way we use them from a vendor and a supplier, a hardware supplier viewpoint is that we are going to aim to abstract away a lot of that physical layer complexity from the end user and just provide them a way of executing what they understand quantum algorithms to be without needing to think about individual error rates, connectivity of qubits, and those sorts of questions. So it's a lowering the barrier to entry question in my mind, and the best way we can help onboard new people to the technology.
Now, Dell is an unquestioned leader in computing. How do you see these two worlds kind of coming together?
Yeah, that's a really exciting question because that's something I think about a lot. One point I would bring up is that we are working closely recently with NVIDIA. Well, we've been working closely with NVIDIA for a while, but in the context of quantum computing, we've been working with them. And actually, they have designed a new framework called NVQLink, which of course sounds a lot like their NVLink, right? And the idea is that NVQLink is there to drive the latency between the quantum world and the classical world down as low as possible. And that's going to allow us to do more things with QPUs than we've been able to do previously, including calibration, dynamic circuits, these kinds of questions. And recently, we were able to achieve a sub 4 microsecond latency using NVIDIA's NVQLink on a number of our PowerEdge servers. So we're really looking at what the technology needs in terms of specifications and hitting those targets to make this infrastructure usable for real quantum computing.
That's a great example of an advancement that bridges the gap between conventional and quantum. When you take a look at the future, how do you see the best scenario for quantum accelerators to be fitting into those conventional systems?
Yeah, the funny thing is that it will start to depend on what type of quantum computer gets adopted for any particular use case or any particular data center. They all have their own challenges, whether it's cryogenic cooling, dilution refrigeration, whether it's vacuum chambers, laser controls, these kinds of questions. And I think they each have challenges when it comes to really marrying them closely to HPC. So it's right now a case-by-case basis. But again, as these things mature and as the QPU vendors become able to support these things in a more user-friendly way, I think the demand on traditional compute users will become less, and we'll be able to see more seamless integration.
Awesome. So what specific compute will quantum reach that is unreachable by today's compute platforms?
Yeah. I know that the commonly quoted answer is things like cryptography, and that's true. There are implications there, and these famous algorithms, Shor's algorithm, Grover's, et cetera. But one that I really think about a lot is the case of molecular simulation. So when it comes to pharmaceutical research, drug design, material science research, there's applications in farming as well. The idea of understanding the behavior of molecules at that really atomic level becomes extremely, extremely important. To actually understand how two different compounds are going to interact with each other, you need to understand their quantum properties. And quantum properties are very difficult for classical computers to model. But QPUs happen to already be speaking that quantum mechanical language. So when it comes to modeling those molecular interactions, actually, you're already speaking the right language when you go to a quantum device. And the ability we have to do that sort of simulation, given a properly configured and sized quantum computer, becomes a lot more efficient. So you'll see real significant disruption, I suppose, in things like material science, drug research, those areas.
Now, from a deployment standpoint, we're at data center dynamics. We think about quantum going into data centers. But do you see that as the primary market where they'll go, or are they going to stand-alone somewhere and have their own environments?
I think they will definitely primarily be augmentations to data centers and HPC environments. I think that will be the primary use case, especially early on. And that's because, you won't be looking to go to a quantum device to you won't be accessing one from your smartphone, probably. You won't be using it to optimize, your local Facebook algorithm or something. It's really primarily, or especially early on, going to be for these large research, compute-heavy tasks like I mentioned, but then also applications in climate modeling. I'm thinking of the traditional HPC tenants. So I think that going to a quantum computer before you've attempted to use, classical HPC or large data center environments is a bit like trying to run before you've walked. Mm-hmm. Exploring what's out there already will be the first key. And only once you've hit those limits in your data center, in your HPC environment, will you start to think about what quantum can do that you can't currently do.
So looking ahead, what really needs to happen both technically and operationally for quantum to move kind of from research-driven all the way through to something that can be deployed at scale?
Yeah, no, that's a great question. And I think it's really twofold. There's software questions and there's hardware questions, right? And software questions are ones that are being asked and answered right now. You have various different frameworks for programming quantum devices. IBM maintains Qiskit, which is an open source project to help you program for QPUs to use quantum gates, quantum algorithms. And recently there have been efforts to abstract that away from right now we're almost writing in quantum assembly, the assembly code for quantum devices, because that's what's maintained. But as the use cases begin to mature and provide more advantage, you'll see an incentive for the market to start to abstract to higher levels. And once we see that Python level abstraction for using quantum devices or even application specific programs, then I think you'll really begin to see a larger adoption, because again, that barrier to entry will be lower. On the hardware side, again, it's modality dependent. What are you supporting a vacuum chamber? Are you supporting a dilution refrigerator, et cetera? But some of these particular trends that we're seeing will cross into all of these domains, into all these modalities. One is questions around cabling. So right now, if you're using superconducting qubits, you need to run analog signals to each individual qubit and occasionally to the couplers as well in there. And for 25, 50, 100 qubits, that's okay. Once you get to 1,000 qubits or 1,000,000 qubits, that quickly becomes a problem you need to solve. And there's a lot of different approaches there. There's ideas of putting small classical components inside the dilution refrigerator. That obviously generates heat. You need to figure that out. Or there are ways of doing more multiplexing. Again, a lot of approaches, but cabling is one of those questions that I think we'll need to address from a hardware standpoint.
Burns, it was awesome having you on the show. I learned a lot, actually, a ton. And we'd love to have you back sometime. Thank you so much for being on. And one final question for you. Where can folks find out more about what Dell's doing in this space and connect with you and your team?
Yeah, thanks for asking. So we maintain a hybrid quantum classical computing page, HQCC, on the Dell.com website. I encourage you to check out the good work that we've been doing with NVIDIA, as well as with partners QEra, IQM, IIQ. There's links on there for all of those, as well as some joint research we did with Ernst & Young. And as well, check out our Dell blog, where we talk about our NVQLink latency results and other cool quantum computing and other topics.
Well, thanks so much for being on the show. And Jeniece, that wraps another episode of Data Insights. Thanks so much for being here.
Thank you for having me.
Thank you.